Now let's do a little bit more with the vibrating string problem. Partial differential equation, boundary value problem. We solved this in, we solved this boundary value problem in a previous recording. Corresponds to the vibrating string. Here's the partial differential equation that models the physics of the string. These boundary conditions say it's attached at a height of 0 at each end. And these initial conditions say what the initial displacement of this vertical displacement of the string is and what the initial vertical velocity of the string is. That's the problem. Here was the solution. And we already did one example where we were actually given explicit f function and g function. And that amounted to a lot of evaluating an integral. In fact, it was more of a evaluated integral problem than it was a solve a partial differential equation problem. Let me do another example that gives you initial conditions that you don't need to take an integral for. This will be an example of what I have been calling the simple method, which I introduced when we talked about, let's see, the heated rod problem. Let's say you have the same boundary conditions on X. So X has a length of 1 unit here, and it's attached to both ends. String's attached to both ends, just like, so we're solving the same, we don't need to resolve the problem. Same solution. L equals 1 because we see this 1 here. We're given the initial displacement, which is this function here, and the initial velocity, which is the derivative of the u, which was the vertical displacement of the string. Its time derivative at time 0 is 0. So initial vertical velocity is 0. That means, go back to the formula, when this g of x is 0, which is the initial vertical velocity 0, all the b's are 0. So we're just left with this part. It's the bend cosine. Actually, what was that solution again? A sub n cosine of the t stuff times the sine of the x stuff. And in our case, L was 1, so we're just going to have a sub n cosine. Let's see, what do we have? L was 1, so just n pi at and n pi x for the sine. At time t equals 0, this cosine is just 1, so it's just a sub n sine of n pi x. So anyway, here's the solution at time 0. That has to equal our initial vertical displacement, which was given this way, sine something. See that this is in the same form as this infinite sum. So we don't need to take an integral. So don't get busy always just taking integrals. Just match coefficients. Here, the n is 3. So a sub 3 equals 0.01. And for all other n, it's 0. So this infinite sum is just one term. 0.01 cosine of that, n is 3 pi at, sine of 3 pi x. There's our solution. We didn't have to take an integral. A couple of things I could say, these are kind of interest. from the physics of the wave equation. I'm not going to go through all this, but interpreting the A in the original problem statement, that's what wave metric. Let's go back to the problems. This A, if you look at the units of the problem, it would correspond, A would correspond to a speed. Speed of what? That's what I'm not going to go through, but it's the speed of the wave. It's the wave speed, which is kind of complicated to explain. I leave that in my written notes. I don't make my students responsible for that. The other interpretation, let's go back to the solution. This thing here, you could rewrite that using a trig identity as just in terms of just pure cosines with a phase shift or pure sines with a phase shift. So that, take my word for it, for n equals 1, remember n equals 1, all the positive integers, 1, 2, and up. N equals 1, that's called the first standing wave, and that corresponds to the whole spring vibrating. And that's the, if you played a musical instrument, that would be the primary note that you hear. The other ends give you these different waves. First, the length divided by 2, and then the length divided by 3, etc. And these other ones would be the harmonic frequencies. This first one, this fundamental one, is called the standing wave, or the fundamental frequency. Anyway, that finishes up the wave equation as far as I'm going to cover it here.